I'm Laura Manner, and today I'll show you how to use Neo4j Graph Analytics within Snowflake to power predictive maintenance in a manufacturing environment. A single machine failure on a production line can cost over $100,000 per hour. Luckily, we can use Graph Analytics to answer questions like, which machines are most likely to fail soon? Which ones sit on critical paths in the workflow? And if a bridge machine goes down, what's our quickest reboot? While traditional models struggle with these kinds of complex intertwined flows, a graph model can solve them in seconds. Our approach is simple yet powerful. Load your tabular data into Snowflake, choose from a suite of graph algorithms provided by Neo4j, and then write the results back into Snowflake tables for easy querying and additional analysis. Plus, all of this runs on a pay-as-you-go serverless engine that benchmarks up to twice as fast as any other open source graph solution. So let's take a minute for a quick overview of the architecture. We start with your raw data in standard Snowflake tables. Then we spin up a compute session. Behind the scenes, Snowflake projects your data into a graph using a SQL query that you provide. Then the Graph Analytics engine runs various algorithms asynchronously. Finally, you can write the results back into Snowflake tables so they're ready for dashboard alerts or deeper analysis. And then finally, when you're done with your session, you can just tear it down with a single call so you only pay for what you actually used. Before we dive into the demo notebook, I wanted to take a moment to talk about the Betweenness Centrality algorithm. Betweenness counts how often a machine lies on the shortest path between a pair of machines. This algorithm reveals hidden bottlenecks that simple volume or degree counts miss. So for each pair of machines, we identify the shortest path between the two machines. Then a machine earns a point if it falls on the shortest path between two pairs. Finally, we add up points for each machine to get the betweenness score. A high score for machine indicates that it's a bridge. A failure could break two whole sections apart. A low scoring machine might have alternate routes, so its failure stays local. We're going to go through betweenness on a toy example to get a better sense of what is happening when we run the algorithm. Here we have a simple graph. As a reminder, we have 4 steps: enumerate pairs, identify and list shortest paths, generate credits or points for nodes on the shortest paths, and sum up these credits for each node. The first thing we need to do is enumerate each pair of nodes. You'll notice that we do not have a pairing for A to B. This is because we're using a directional graph. So A goes to C, but C does not go to B. So there is no path between A and B. Now that we have identified all the potential paths on the graph, we then identify the shortest path for each pair. Note that for many of these paths, there is only one option. For example, the path from A to D, you can only have A, C, D. There is no alternative. However, if you're going from A to F, there are 2 potential paths. You can go A, C, D, F, or A, C, E, F. For the purpose of betweenness, we want to make sure we note each potential path. Next, we'll generate the credits for the nodes on each shortest path. So for the pair A to C, you'll notice that no machine actually falls in between A and C. So no machines get points. However, from A to D, we have C in the path, A, C, D. So we give C 1 point. In the case when there are 2 options for the shortest path, we'll have to calculate these a little bit different. So here we see that A, C, D, F. So we have C and D falling on the shortest paths for one option, and C and E falling on the shortest path for the other. So since we have 2 potential, each will get half a point. If we had 3 different paths, each would get a third of a point. So C gets 2 half points, so C gets 1 point. D has 1 half point, so it gets a half. And E has 1 half point, so it also gets a half. Finally, we can sum up all these points, or credits. So A, B, and F don't get any points. They're all terminal nodes, meaning that they will not fall in between 2 nodes on the shortest path ever. D and E have slightly higher at 1.5. They're a little bit more on the path, a little bit more between things, but the highest betweenness score comes from D with 6. So to recap, we first enumerate the pairs, list shortest paths, add credits between nodes, and sum each node. However, doing this calculation for a very large graph doesn't make much computational sense. So the graph analytics implementation from Neo4j is based off of Brand's approximation theory for unweighted graphs, allowing for more efficiency with large graphs by sampling nodes and only calculating a certain percentage of them. Now that we've properly set the stage, let's walk through the notebook. Everything has already been executed, so we're just going to scroll through, talk about some key steps, and interpret some results. Now, before we dive in, if you want to follow along, you will need to install the Neo4j Graph Analytics app for Snowflake from the Snowflake Marketplace. You'll also need to create a Snowflake database. We're using m_demo. Next, you'll have to ensure that you have access to read and write capabilities to and from the database and the proper compute resources. That code is taken care of here. It's really important after you create them to switch back to the GDS role so that you don't run into any permissions issues. Next, we'll add our data to the database. If you're using data from an existing Snowflake database, you can skip this step. Here, we're creating two tables. We're loading the nodes. The nodes are the machines. You'll see we have machine ID, type, current status, and risk level. Here are our relationships. We have source machine ID, destination machine ID, and throughput rate. In order to prep the data for the graph, we'll have to make a few adjustments. It's very important that you create new tables for this with just the information needed. So for the nodes table, we're going to have just the machine ID as node ID. This label with all of its capitalizations is important. Same with relationships. We're specifically going to want source node ID, target node ID, and then we have total amount here. This could be something different, but the most important thing is that you have node ID like this, source node ID like this, and target node ID like this. So now we can start running algorithms. Each algorithm, when you call it, you project your graph right here. So you can see here when we're calling weakly connected components that we're using the m_demo public database. We're using the nodes view that we created, not the original one. So this is the one with just node ID as the label. And then we have the relationships. And then source table, we're going to put the nodes, and target table, we're putting the nodes, because it's trying to match up which nodes are coming from where. Then we just need to make sure we add right components for this one. So here we want the node labels to be focused from the nodes view, and that our output table is going to this nodes WCC table. This will be a brand new table. After we run it, we can look at our results. So for WCC, for this type of analysis, we really only want to see one component. If we had multiple components, that would mean that the graph itself was not fully connected. So then we get into PageRank. See how similar this is? For the projection, it is exactly the same code. Here, though, we're going to want to add a score because we want to be able to look back at this. So we'll have compute. We're going to mutate the score property. And then we're also going to create an output table, but this time we're going to include the node property score. And then you can see when we run it, we have this score here. So the node 20 has the highest score of 1.5102. This makes sense because the 20 is the terminal point and has the most connections. Let me pull up a view of this. So here you can see 20 is a lot of importance. It's the last node on the line, and it has 5 incoming nodes. So it's extremely important. So if we come back to the code, let's move on to Betweenness Centrality. With Betweenness for the API, it's very, very similar to what we had for PageRank. The projection's exactly the same. And then we also have the mutate property for score and node property for score. This time when we get the output, You'll notice that 20, even though it was ranked the highest of importance with PageRank, for Betweenness, it's not anywhere because as we talked about earlier, it's a terminal, and terminals do not get high Betweenness scores. Here, instead, we have 13, 14, 15, and 3 as the highest scoring Betweenness. This is because if one of these breaks, it completely disrupts the ones before and after. And that's it. We went from raw production data to risk-ranked insights with just a few SQL calls. We verified that our network is fully connected. We identified hubs and bridges. Now, when we end this session, the compute shuts down and results stay in Snowflake. So you won't be charged for anything besides what you've done in that session, but the data that we got from that session is ready for dashboards, alerts, or deeper analysis. Thanks, and happy graphing.